For today's task, we were asked to give an example of dynamic programming that was not from the lecture. And when I was looking at the different algorithms, one of my favorite ones that I come across was this coin change. And the key here is the coin change with dynamic programming, because there's the coin change algorithm without. And we'll kind of compare the two and then talk about actual usage with this algorithm and why dynamic programming is so powerful. And there are some sources below. So the main problem this algorithm tries to solve is how do I get the fewest coins to make the desired total? And really, coins is in quotes here on purpose because it could be the shortest path to the target with the the input values, and I'll explain that here in a minute. But I use coins to make this simple because it's called the coin chain algorithm, but you'll see different inputs to get the desired target. We'll see how that's used with dynamic programming. So, like I said, I want to show the power of dynamic programming versus like not, and how with the dynamic programming, the coin change algorithm is better versus the greedy version of this, and the benefits and everything. So, here's a good example is if we have a target of 26, and backing up just a little bit, before we know the target, we have to know the input of what values we need to get to that target. So for example, in this one, to get the target of 26, we know we have the coin denomination, so to speak, of 1, 2, 4, 8, 13, and 23. And the question we want to solve is what's the fewest coins possible or inputs possible to get to the final target number based off of this input. And we'll see how a greedy version of this would work versus the dynamic programming version. So the greedy version of this would always look at the highest value closest to the target. Highest value closest to this target first and use that first to see if we can get to 26. In this case, it's going to look at 23, and then I'll look at 2, and then I'll look at 1, add the sums to get to 26. So I want to make sure I mention here, to get to the target, that's what this any dynamic programming algorithm, or I shouldn't say any dynamic programming algorithm, but especially the coin chain algorithm, will take the values that we have, sum them up, and we'll talk a little bit more about it, but we'll kind of see every path to get to the target and keep track of that in order to see what the shortest path is. So if this was the greedy version of this without the dynamic programming, would have 3 values, 23 plus 2 plus 1 to make 26. But you'll see we can get the target quicker by just doing like 13 plus 13, or only requires actual two numbers or 2 coins to get there. But the greedy version of that doesn't care if there's a shorter path. It just looks at the highest number first. As I mentioned with dynamic programming, what it's going to do, and I'll show a little bit more of that in a minute, but it's going to look at every possible way of getting to 26. And when it goes through its iterations and goes through the different routes, it's going to learn that there's a quicker way than just 23 plus 2 plus 1. It's going to say, okay, I have a denomination of 13, and 13, 13 make 26. So I only require 2 coins to get to this final value. This is used by ATMs and banks in real world situations. Although most ATMs do only give $20 bills now, It can be used by a cashier to figure out, like, if I need to get $50 worth of change, how would the best way to get that, 20, 20, 10, whatever. Um, this algorithm can be used to give you the exact coin amount that you need. Um, so another major benefit of dynamic programming is the ability to store subproblems. For example, in the last target of 26, it would remember that 13 plus 13 is 26 for our future target of 26, or exactly 26 again. So really explain this further. It's not like it stores essentially the sum is a simple way of looking at this, but in reality, with it being a coin change coin change algorithm, it's going to store the needed value for the number of coins as what it stores in a hash. Meaning that in this case of my target of 26, we know that the algorithm knows now that you need 2 coins to make 26. So the next time you have a target of 26, it's going to automatically give you an output of 2 because it knows what the input is. And so the next case, if you had like 26, it's going to know, or sorry, 27, it would know, okay, well, 26 was 2, so I'm going to start at 2 and see if I can just add another number to get to my 27, and so on and so forth. I'll talk more about this in a minute, but if it's not possible, it will return a -1, and that's how we can get an error message to know, hey, this value is not possible. Like I mentioned before, it keeps the results of the subproblems of the sums in hashes, so they almost must be solved once. If it's already been calculated, and the same number is required again, for like the number of coins needed will be immediately returned. So if I had the first target as 26, like I mentioned, and it does all its math to figure out the shortest route, and figures out the shortest route with the input is 2, the very next time that the target of 26 is required, instead of doing all the math again, it's going to say, oh yeah, you need 2 coins. So has outer loops and inner loops for each coin. That's kind of the way it's structured. And for the worst case time complexity, it's O of n/a. An example of that would be if we only had 1 coin to get to the target. So like if we have the target of 26 and we only have a coin, like a penny, for example, it'd take 26 pennies, and that's one way we would get to the worst output. So here is a kind of simple version of how this works with the target and how it keeps track of everything. As I mentioned, it looks for each possible route to the target number. For example, if the target is 8 and we have 134, there's all the possible ways to get to that, and it's going to keep track of all that. It's like, okay, in the first case, it took 8 values, then it took 6 values, then it took 4 values, then it took 5 values, then it took 3 values, then it took 2 values. And of course, it's gonna, when it goes through all that, it's gonna look for the shortest path, and it's gonna know 2 values was the shortest, and it's gonna output, hey, you need 2 coins for this case. And it would keep track of all that. It would keep track of that as well, of like, okay, we have all these ones, have all these different ones, and that's how it's a lot faster because it keeps tracks of this in hash values. So edge cases are different cases that we need to talk about, is like worst cases. For example, first edge case I have here of like is that if the target is 0, it can handle that. It knows that if the target is 0, it's just going to be 0. If it's impossible, the algorithm will turn -1 and give us an error message. Worst case is only having one coin to get the target. And the other impossible would be if all coins are larger than the target. So if the target's like 25 and the smallest coin I have is 50 cents or whatever, there'd be no path to get to there, so it would return -1 for an error message. So summary of this is the coin change algorithm with dynamic program keeps track of subproblems to kind of help faster processing. So if the target's the same multiple times or similar multiple times, it doesn't have to do a bunch of math again. The worst case is one coin. In possible cases, returns -1. And as I mentioned, because the subproblems are stored, it will automatically know what the fewest coins possible will be for a similar target or the same target immediately after the first iteration of this to determine how many coins are needed. Thank you so much for your time, and I hope you learned something about the coin change algorithm with dynamic programming. And I hope you have a great day.